All right, so we're going to go ahead and get started. So good afternoon, everyone, and good morning to those joining us from the West Coast. Thank you all for taking the time to be here today. We're really excited to have a fun discussion, clearing up some FAQs and exploring facts about lab-grown and natural diamonds. My name is Sherry Woodring, and I'm thrilled to be here today with my colleague, Kayla Endy. She's a highly skilled gemologist and diamond grader. So Kayla, why don't you take a moment to introduce yourself?
Thanks, Sherry. Hi, my name is Kayla Endy. I've been with GCal for almost 3 years now. And one of my favorite things to do here at the lab is take photomicrographs and do some inclusion photography. And I'm really excited to share some of those photos with you later in this presentation.
Thanks, Kayla. And I've been with GCal for 19 years. Lab-grown diamonds have been a particular area of interest and focus for me ever since they entered the scene in the early 2000s. Today, we're going to do this presentation. We're going to start with some fact or fiction questions, followed by a deep dive by Kayla into the nuances of color and clarity grading. Our audience's diverse range of experience, so we'll aim to provide a little of something valuable for everyone. So feel free to put your questions into the Q&A box at any time, and we'll get to them at the end of the presentation. So we're going to get started today with an easy one. True or false? Lab-grown diamonds have the same chemical, physical, and optical properties as natural diamonds. This is true, of course. So one of the most frequently asked questions is, are lab-grown diamonds real diamonds? And the answer is yes. They have the same chemical, physical, and optical properties as natural diamonds, but they're man-made in a machine instead of the earth. Both natural and lab-grown diamonds consist of carbon atoms arranged in a cubic crystal structure, and this defines their chemical identity, regardless of their origin, and distinguishes them from their simulants, such as moissanite and CZ, which are composed of entirely different elements. Simulants should never be referred to as lab-grown diamonds or synthetic diamonds. So when the carbon atoms are arranged in any other structure, not a cubic crystal structure, then they're a different material, such as graphite or amorphous carbon, which is here when they're arranged in this random structure. So we actually see amorphous carbon on the edges of CVD crystals as they're growing. So the center is a single crystal diamond, and this is in the shape of the wafer or the seed. And then as it grows, this non-diamond carbon ends up around the edges like this. So the cubic arrangement of carbon atoms contributes to diamond's remarkable properties, including its chemical properties, such as resistance to corrosion. In life, we see these properties that diamonds are exceptional in cutting tools, even under really extreme conditions. And diamonds are also being researched for several different medical applications in the future. Natural diamonds and lab-grown diamonds also have the same physical properties, such as hardness, toughness, density, and thermal conductivity. So in life, this makes them very valuable as heat sinks in high-powered electronics, and in the future, maybe quantum computing. But more importantly for us in this industry, as the hardest material, they're ideal for engagement rings that are worn on the hand every day. And on the Mohs scale of mineral hardness, you can see diamond is by far much harder than corundum, which is a 9 on the scale, diamond's 10. So it's actually diamond's 4 times harder than corundum. So what does this mean? What does this mean? How do we see this? So this is an example of my friend's ring. She wore it every day for many years, and you can see that the sapphire has so many scratches and chips around the crown. Even though this is a 9 on the hardness, it's still over years of wear, it'll definitely show the wear and tear. And this is an example. This was an interesting ring that was sent in for identification. This is a 10-stone band. 2 of the stones here are diamond, and the other 8 stones in the band are moissanite. So this one here, and this is the same diamond. We just turned the ring a little so you could see the surface. So moissanite's 9.25 on the Mohs scale. But you can see like this, every single moissanite in this ring is really destroyed compared to the condition of the diamonds. So that's the physical property of hardness. And lastly, the optical properties of natural and lab-grown diamonds are the same. This is a subset of the physical properties, but it deals specifically with how light interacts with the material. So this is like refractive index and dispersion. So in life, how does this look? These are fire videos showing examples of the different levels of dispersion that we see in simulants and in diamond. Okay, next question. I'm selling a lab-grown diamond, and a diamond tester will definitely prove it's a real diamond to my customers. So first of all, it's better not to use the term real diamond. It's better instead to say a lab-grown diamond versus a simulant. But the answer here is really you need to use caution. So let's talk about how diamond testers work. These devices are designed to differentiate between diamonds and simulants like CZ or moissanite. They can be useful, but they're not foolproof, especially when you're dealing with lab-grown diamonds. So they operate on two principles. There's diamond testers that operate as thermal conductivity or electrical conductivity. And in some cases, they measure both, a dual tester. Diamonds are excellent thermal conductors. So the probe measures how quickly heat travels through the stone. A diamond will conduct heat much faster than simulants, and it will show that it's a diamond. Electrical conductivity measures the electrical resistance of the stone, and diamonds are electrical insulators, and most of the simulants are conductors. But these testers should work to separate natural and lab-grown diamonds. Problem is there's a few things you need to be aware of and use caution. One, it's just not all of the testers are created equal. Some are $15, some are a few hundred. And if the testers have to be used properly and be in proper condition. So you have to make sure the stones are clean, the probe is clean, you're not hitting metal. But even when you have a good quality tester and you use it properly, there are some other issues. Newer moissanites can actually have similar properties to diamond, and they'll produce a diamond result. So you could have a moissanite and the tester says diamond. But then you also have lab-grown diamonds that and some rare natural diamonds that contain boron, which makes them electrically conductive. And these diamonds will test as moissanite with the tester. So moissanites testing as diamonds, diamonds testing as moissanites. It really can be a mess. So we don't recommend that you use this in front of a customer. Okay, so next question, true or false? Lab-grown diamonds are identical to natural diamonds. False. So I just explained how their properties are the same, but they aren't identical because their origin stories are vastly different. So let's just talk a few minutes about the origin differences and how diamonds are grown. Natural diamonds are incredibly ancient, anywhere from millions to billions of years old, and they form through a very complex and lengthy process. It's estimated to take anywhere from 1 to 3 billion years under extreme conditions, intense heat, pressure, 200 miles beneath the Earth's surface. And the conditions are very volatile with fluctuating temperatures, different pressures, and there's various elements which lead to trace impurities in the structure. So all these varying conditions create intricate growth patterns similar to the way we see tree rings in a tree. So we see a complicated pattern, and we can observe this in high resolution short UV imaging, such as the Diamond View instrument. Now the HPHT method, it is meant to mimic Earth's intense heat and pressure, but it's under very consistent and controlled environment. So tiny diamond seeds are placed in a chamber alongside a carbon source such as graphite. And then there's this molten metal flux containing elements like nickel and iron that surround the seeds and help distribute the pressure and heat uniformly. So this is a controlled growth, but under immense pressure and heat. The CVD method is more like a microwave method. It's like ice that forms from rain. So the plasma cloud is raining carbon atoms. So we have here this platform. This is the seeds of CVD, the wafers that you start with. The purer, the better, higher quality the seeds, and the higher quality the gas, the better resulting CVD diamond, better quality. So you have this carbon-rich gas that then is broken down into a plasma by microwaves, and these freed carbon atoms rain down and they adhere layer by layer onto the diamond seeds, and it gradually builds up into a diamond crystal. That's the basic method of growth. So this environment in which they grow is directly reflected into the growth patterns that we can observe and often in the inclusions that we see in a diamond. So these 3 photos were taken in our Diamond View instrument, and they show the different surface fluorescence and the evidence of their growth methods. So this is a very complicated natural growth pattern. This is a blocky, kind of a geometric HPHT growth pattern, and this is a layered CVD growth pattern. So in addition to their unique growth patterns, natural and lab-grown diamonds can also be distinguished by their nitrogen content, which shows up in their spectral analysis. So type 1 diamonds contain nitrogen, like this, and type 2 diamonds don't contain nitrogen. So we can see that in this area of the FTIR spectra here. On these graphs, you can easily see the difference. Nitrogen's abundant in our atmosphere, and so it's a very common impurity in natural diamonds. So let's just talk a little bit about type 1 diamonds that contain nitrogen. So when nitrogen first gets into the crystal lattice and replaces a carbon atom, it starts as a single nitrogen atom like this. But when there's single nitrogen, the stone is going to be yellow. Okay. But natural diamonds are type 1A instead of this is type 1B where it has a single. Once the nitrogen in the structure has had a chance, it's under the ground, it's millions, billions of years, and these nitrogen atoms have time to kind of make friends, and they come together in clusters of 2, 3, 4, and this is how we get type 1A diamonds that make up about 95% of all natural diamonds. So in contrast, lab-grown diamonds, much shorter time period, and the nitrogen, if it's present, which very often it's not, because like CVD diamonds are grown in a vacuum, they don't want nitrogen in there, so they don't include it. But if it is, you're going to get a yellow diamond. Okay. So we just talked about nitrogen in clusters of 2 or 4, but when nitrogen's in groups of 3, it's a different defect known as the N3 center. So we see this defect when we use visible spectrometers. And this is important to know about. This N3 center shows up as a 415 peak. It's also part of the CAPE spectra that some people talk about, the CAPE spectra with N3 nitrogen. And many of the screening devices on the market work by this principle to separate natural from lab-grown diamonds based on this N3 center. So these 2 spectra were collected when the diamonds were excited by white light. But when we use instead fluorescence or UV light, and we take a spectra, then we get an even stronger, more distinct spectra of this N2, N3 series. This is similar to how the ID 100 or the EXA instruments work. Okay. So next question, true or false? My diamond has blue fluorescence, so that means it's a natural diamond. So actually, this is pretty true. You have to be careful. You have to know what you're doing, but it's true. Using a long wave ultraviolet light, like a standard gemological lamp, lab-grown diamonds in the D to K color range, they don't fluoresce blue. We've examined millions of lab-grown diamonds, and we haven't seen the same type of blue fluorescence, the kind that we're all familiar with in natural diamonds. It occurs in 25 to 30% of natural diamonds. We don't see this type of fluorescence in lab-grown diamonds. So remember that N3 center we were just talking about? The N3 center is responsible for the blue fluorescence that we see in most natural diamonds. Maybe you ask, well, then why don't all diamonds fluoresce blue? Well, that's because some of the other defects in diamonds, like an A center, will actually it gives a different outlet for the energy to escape, so it doesn't have to come out as fluorescence. So that's why we only see blue fluorescence in some natural diamonds. So when you're using fluorescence, it's a great tool, but you have to understand the different wavelengths. So we're talking about here long wave light. This is the standard light used for grading fluorescence in diamonds. And most gemological lamps will have 2 different wavelengths of light, a short wave and a long wave. Fluorescence is only a good supplementary test, a good indicator. You really should never use it as the only identification, but it's very helpful. So we recommend that you use something like a dark viewing box like this. let your eyes adjust to the darkness before you're judging the color of the fluorescence. And it's great. Like, let's say you have a tennis bracelet, you put it on the UV lamp and you can quickly get an overall idea of what you have. If you've got a mix of none to strong blue, maybe a few yellow or orange, it's probably a natural diamond bracelet, just as a quick first check of identification. If you have something where none of the stones are fluorescing, or you've got one or two that are fluorescing reddish, orange, it might be a lab-grown diamond bracelet. And then if you've got them fluorescing all the same kind of a yellow and you turn it to shortwave and they're all a little bit stronger yellow or orange, it's probably a CZ bracelet. But that doesn't identify each individual stone. It's just kind of an idea of what you're looking at. It's a good starting place. So natural diamonds, like I said, they can fluoresce a whole wide range of colors due to different defects and impurities. Most often blue, such as this ring here. It's got blue fluorescing diamonds. The lab grown under long wave, no fluorescence at all. Under short wave, this picture is kind of extreme, but occasionally under short wave, you will see orange, yellow type of fluorescence under a short wave light for lab grown diamonds. These are examples of HPHT grown diamonds that have varying degrees of orange fluorescence under long wave. So fluorescence is while the long wave light is on. Once you turn off the light and it continues to glow, that's called phosphorescence. So these diamonds have both fluorescence and phosphorescence to long wave light. This is actually pretty rare. Maybe less than 1% of HPHT grown diamonds have this effect. So now let's talk a little more about phosphorescence. Let's say true or false. If my UV screening device shows a stone with phosphorescence, then it means it's an HPHT lab-grown diamond. No, that's false. So screening devices are using short-wave UV light, not long, it's short-wave, and natural HPHT and CVD diamonds can all show phosphorescence. So that's why these instruments show a result of refer. It means you have to do further testing to confirm what you have. So the examples on this slide show what is most common, the reaction we normally see. These were taken in the synth detect instrument. It shows the common types of fluorescence, phosphorescence that we see with these screening instruments, but it's never a full identification. It's just an indication of what you might have. So if your screening device says refer, get it checked. Don't assume it's a lab-grown diamond. This is a picture of the famous Hope diamond, which has red phosphorescence to shortwave. But actually what's more interesting in this picture is the one diamond in the halo that has phosphorescence. This is a natural diamond and it's phosphorescing under shortwave UV. Okay. So remember these three orange diamonds? So under long wave, they have orange, fluorescence, and phosphorescence. But under short wave, these same three diamonds have this very strong, typical teal glow, this phosphorescence and fluorescence under the short wave UV. Okay, so last true or false. Lab-grown diamonds can be grown any color. This is false. HPHT diamonds can be grown yellow to orange colors. Usually intense to vivid type of yellows. They can also be grown blue in a range of shades ranging from light to nearly black. CVD diamonds, they can be grown pinkish, kind of like this light pink color here. Also in shades of brown and grayish blues. But most commonly, the fancy colored lab-grown diamonds in the market are treated. This is a post-growth combination of either irradiation and annealing or both. We see both HPHT and CVD grow diamonds that have been post-growth treated. So you might think like, oh, HPHT diamonds can be grown blue. So all the blue HPHT diamonds must be as grown. Actually, a lot of them are treated. And it's important to know that because when they're treated by irradiation, the blue colors, they will change color with high heat. So any color enhanced, whether you've got natural or lab grown, any color enhanced diamond, you should be careful and handle them with care, no high temperatures. see what else. Also, the irradiated colors that we see in terms of blues, very often they are a greenish type of a blue. Almost all the pinks on the market, any of these intense, vivid pinks, they're all treated post-growth colors. Okay, and the yellows that we see that are treated, they're often more of a honey colored, a warm brownish, orangey yellow. But they also can be a pure yellow that looks very much like a natural yellow color, but they could be treated. Okay, so I'm going to pass it back over to Kayla now to talk about the nuances of color and clarity grading.
Okay, thank you so much, Sherry. Let me just get this up over here for everybody. How do we look, Sherry?
It looks good. I can see your screen.
Awesome. Thank you so much. So I'm going to talk a little bit about the nuances in color and clarity between natural and both types of lab-grown diamonds. But before we get into that, though, I want to take a moment to look at some of the trends that we've seen in our lab over the last number of years with regards to color and clarity and the averages that we've seen in lab-grown diamonds. The first graph here that I want to show, and as a note, when you're looking at the colors, the red that you're seeing is the highest concentration and green the lowest. And nearly a decade ago, in 2015, the trends we were seeing in color and clarity was relatively low. We were looking in the J to K color range and the SI2 to I1 clarity range. But as we move into the next year, 2016, already we're seeing some pretty big changes. There's much more of a range here, and the most common qualities are a lot higher in color and clarity. So this year, the most common qualities for color were H to J, and for clarity, it's really starting up in the VS1 range over here and then going down. In 2017, it's relatively minor changes, but the most important thing to note here is this sort of tightening up of the range. The highest color and clarity concentrations we're seeing are around the same area, but there's a lot less of the lower color and lower clarity stones. All of these red areas that were previously down there have sort of turned into yellow. And in 2018, this trend is continuing. Again, more of a tightening in terms of the frequency here, more of a concentration around these qualities, this kind of IVS1 area, and less of the lower quality stones every year. Now, in 2019, we started to see a pretty interesting shift, and that is in part due to what happened in mid-2018, which was when De Beers announced their entry into the lab-grown space. This caused basically a green light for site holders and a lot of major manufacturers to enter the space as well. And they brought along with them expertise in manufacturing and significant capital. And so we started to see a pretty big shift at this point in color. So while the largest red concentration that you can see here is sort of in the same area, we're starting now to see the red sort of moving over into these higher colors, even in the G, even F and E area. And in 2020, there is a big shift with the highest concentrations of color moving from the I area all the way over to E, F, and G, which became the most common color range. And this is the first time we're seeing the highest proportion of those stones in that area. In 2021, that concentration is really the same, but the biggest thing that we saw here is you can see this row at the top. We started seeing a lot more internally flawless lab-grown diamonds at that time, as well as more D-color stones. You can see this greenish yellow has turned into an orange color. In 2022, we saw the same kind of thing, more improved color. You can see this now darker orange in the DE area, and a improved clarity range where there's more IF stones, and the overall trend is going higher. So our main range was D to G, VS1 to VS2. And now this is our graph for last year for 2023. We're still improving color and clarity, but much like before, the biggest thing we're seeing here is an improvement in a new section of clarity. We now have this flawless section where we are seeing, again, these higher clarity stones that are being grown. So let's get right into color grading now. The first thing that I want to note about color grading lab-grown diamonds is that we use the same D to Z scale for all diamonds, whether they're natural or lab-grown HPHD or CVD. We use the exact same master sets to grade them, and we determine their grade in the same way, regardless of their origin and regardless of their hue or tone. But on the topic of hue, there are a few things to note in both types of lab-grown diamonds as far as what's out there and what you might see in the market. So we'll start here with CVD. While CVD diamonds are commonly grown to be yellow, historically they've also had a lot of tones of brown, gray, even this orangey pink. These tints have generally been pretty low in tone. They've been brownish and they have what we sort of call this grungy color. But as you've seen with the graph that we showed previously, in the last few years, there has been a significant improvement in not only the grade of the colors upwards, but also in the tone. And so we've seen a lot more of the true yellow, a yellow that is more similar to what you would be used to seeing in a natural diamond. We don't see as many of the unusual hues as many of the orangey pinks or the brown grungy diamonds, but they are still definitely out there on the market. So while yellow is dominant, these sort of pink hues that you see up here, they do exist. They are definitely out there, and it's totally something to be aware of. And as far as the increasing dominance of the yellow tones, this is due in large part to improvements in the growth process for diamonds, but also to some of the post-growth treatment that can be done to them to achieve that more natural-looking yellow hue. And in HPHTs, on the other hand, their predominant, more unusual sort of hue is this blue tint, which has been pretty common historically. There have been other tints that are seen a lot less frequently. We describe them sort of as lemon or mint. And what all three of these have in common is this bright sort of high tone. The blue, as you can see up here, is a kind of pure, clear blue. The lemon was a very bright sort of lemon yellow, as the name suggests. And that has been generally the case across all of them. The blues in particular, something to note is that they can be really difficult to grade in a mounting, really difficult to identify. In part, that's because the blue really kind of disappears when you look at it against a yellow gold mounting. And because it's something that our eyes are not used to looking at, even when they're in platinum or white gold, they can be pretty difficult to detect, even if you're looking through the girdle. So it's definitely something to watch out for. Much like with CVDs, these colors have improved. We're generally seeing stones in the D to F range. And as with CVDs, again, we're seeing a lot more colors that are similar to the typical natural yellow that we see in natural diamonds. But those blues in the kind of E to F range are still out there in smaller quantities, definitely something that you might see out in the market. And since on the previous slides, we looked at some different saturations of the blue and pink, here's just a reference to see what they might look like in comparison to yellow. And again, we're not seeing these hues as often, but it's just something to note. So these are all diamonds in the G to H color range. You'll see a natural diamond with a yellowish tint on the left, an HPHT diamond with blue in the middle, and a CVD diamond with one of those kind of warm tints on the right. And you can see that while the difference isn't enormous, it's definitely detectable, definitely something you're going to want to look out for. And with that, let's move into clarity grading. So before we get into the nitty-gritty there, I just wanted to talk kind of briefly about our GCal certificates. It is common in some other laboratories to refer to inclusions in lab-grown diamonds as growth remnants or internal characteristics. But here we use the full range of inclusion names for both natural diamonds and lab-grown, using generally the same terms. And the reason that we do this is so that it's easier to identify a diamond by the certificate, both for people who are selling diamonds and also for the consumers. But there are a few key things to note here. There are a few key differences between the inclusions and their terminology. I have split these into three categories for us to talk about. The first is inclusions that we only see in natural diamonds. The second are inclusions that we have named differently to avoid confusion. And the third is inclusions that have the same name, but might look a little bit different in natural diamonds, CVD, and HPHT. As with color, something I really want to stress is that we still use the same criteria and the same factors for grading. And for clarity, we have the 5 factors for an inclusion. That would be color, size, location, relief, and nature. So the first section here that I want to discuss is inclusions that we only see in natural diamonds, and there are 3 of them really to remember. The first one is twinning wisps, the second one is etch channels, and the third one would be knots. So starting over here with twinning wisps, they are defined by GIA as a series of pinpoints, cloud, or crystals that form in a diamond's growth plane. And these are typically associated with crystal distortion, or as the name suggests, with a twinning plane. Now, the reason that we don't see these in lab-grown diamonds is because we don't see this twinning or distortion the same way. Both of these phenomena are caused by the variations in the natural growth process, all the different geological forces and all the variations thereof that can happen in the natural growth environment. And while the lab environment, especially with HPHEs, can mimic geological conditions, it is a very hyper-controlled environment. And so all of the distortions and the variations you'd see in natural just doesn't occur in the scenario where you're growing a lab-grown diamond. The next inclusion here is an etch channel. These are hollow tunnel-like inclusions. They start at the surface of a diamond and they burrow or penetrate into the diamond. And research is actually ongoing into these really interesting inclusions, but they are thought to be formed by high temperature fluids or thermal fluids. The reason we don't see these in lab grown is similar to with twinning wisps due to geological conditions. Diamonds are formed not in the Earth's crust, which is the top layer of the Earth, but actually the next one down, which is called the mantle. And before we can find them and mine them, they have to get forced upwards by different geological processes. And it's thought that it's during this journey between the different layers of the Earth that the thermal fluid sort of eats into the diamond and creates these etch channels. And again, since this unique environment doesn't happen in the super controlled environment where they're growing lab-grown diamonds, those etch channels aren't going to form. These inclusions aren't the most common, but they are out there for natural diamonds, so definitely something to be aware of. Additionally, I just wanted to take a moment to compare the etch channels to laser drill holes, which is something else you might see out there. These two things can look similar, but should not be confused. Some ways you can tell them apart are that etch channels have this sort of ribbed or almost worm-like appearance to them. You can see here on the left these little striations, whereas laser drill holes are smooth and they end in an inclusion because the reason that a diamond is laser drilled is to reduce the impact of the color of an inclusion. And the last diamond, natural diamond only inclusion that I want to discuss is a knot. And according to GIA, a knot is an included diamond crystal that extends to the surface after fashioning. And the reason that these aren't seen in lab-grown diamonds is because diamond doesn't form as an inclusion in lab-grown stones. We will look later at the different types of crystals that we do see in lab-grown diamonds, but diamond is not one of them. And since both the inclusion and the parent crystal here, when you're looking at a natural diamond such as this one, are the same substance with the same refractive index, something interesting to note is that they'll very often be largely transparent. As you can see here, you don't see like a totally solid crystal, you're only seeing parts of it. For the next section here, I want to talk about similar inclusions that we have decided to call by different names. There's really only one here to talk about, but it's an important one. It is naturals versus surface remnants. Now, lab-grown diamonds can have pieces of the surface left over after polishing, just like a natural diamond can. But on lab-grown certificates, we don't call them naturals or indented naturals. We call them surface remnants or indented surface remnants. We do this because we don't want the word natural to appear on a lab-grown cert in any form. That kind of terminology we feel could be really misleading for consumers, and so we came up with the term surface remnants to describe them a different way. They can look extremely similar, as you can see here, this sort of ribbed appearance, but something to note is that on the left, you can see this formation here, which is known as a trigon. We have not seen them on lab-grown diamonds, but they are relatively common on natural diamonds, so that can be something helpful to look out for if you're seeing them when you're looking at a stone. I have some more photos here. Here is a surface remnant on the left in an HPHT diamond and on the right in a CVD diamond. Important to note that these are way more commonly seen in HPHT diamonds than in CVD diamonds. And that is because the outer skin of a CVD diamond, as we saw before, is this kind of grainy black amorphous carbon. And since that has to be removed pretty thoroughly before fashioning with a laser, less surface remnants are left behind and we really don't see it as often. You can see here that exact kind of crystal. This is the bit that's removed, and by the time that process is done, it's pretty uncommon for there to be any sort of surface remnant there. And now for the last of those three sections, Same name, different look, inclusions that we use the same terminology for, but might look different. And even though these inclusions may appear differently in natural and lab-grown diamonds, we use the same names because they sort of fit into the kind of the same descriptive category, and they can be pretty easily interpreted through the same lens and the same terminology. There are, of course, other inclusion terms that we use aside from crystals, clouds, and needles, inclusions like feathers or pinpoints. They don't have as many visual differences as the 3 inclusions I listed here, so we're going to focus on these ones. The first one I want to talk about is crystals. So starting with natural diamonds, crystals in natural diamonds can take on a lot of appearances, but something that is unique to these that you will not find in a lab-grown diamond is that they're frequently transparent. You can see in both photos here, it's easier to see in the one on the right, the transparency in these crystals where you can see the light sort of coming through. There's a lot of really interesting variation in crystals in natural diamonds. As we discussed earlier with knots, they can even be diamond, but they can also be other minerals such as peridot or even garnet. Here's a few other pictures of some crystals in natural diamonds. On the left here, you can see one that has sort of an interesting color to it. It's this light sort of brown. And on the right is a crystal that you can see, again, this transparency in it. And it's also an inclusion that's undergone a process that we call graphitization, which causes these dark spots to appear on the surface. In contrast, crystals in HPHT diamonds, they are not transparent. They consist of flux remnants. Shari talked briefly about the HPHT growth method and how the seed crystal is surrounded by this metallic flux to help the diamond form. It is this flux that creates the inclusions that we see in HPHT diamonds, actually. They can sometimes resemble the crystals in natural diamonds. You can see here in particular, might look a little bit similar to some of the crystals on this a couple slides ago, but they are actually metallic and they are completely opaque. They are not transparent. And since they are metallic, a really good way to tell that they are this metallic flux rather than a transparent crystal is to kind of move them around under your light source in your microscope well or under the light you're using with a loupe. They might even sort of change appearance from light to dark. As you can see, both of these photos are of HPHT crystals. This one's very light, this one's very dark. It's because since they're metallic, they're completely reflective. And as you move them around, the crystals can change from white to black completely just based on where the light source is hitting the surface. Another thing to note about these is that when these crystals break the surface, it is really common for them to fall out during the polishing process. This will leave large cavities, and these are a really common thing to see in HPHT diamonds. Here's another couple of photos. These inclusions, they can come in a lot of different shapes, but it's really, really common to see pill shapes or tic-tac shapes. It's really common to see rods like these ones over here, or just blobs like the photo on the right. And the one on the right, this flux crystal, is a really good example of how bright they can be when they're reflecting light from a microscope. In contrast, in CVD diamonds, the crystal inclusions there are actually made over of the carbon left over from the growth process, that sort of dark amorphous carbon that you saw on the outside of the CVD crystal earlier. That's the same substance that we're going to see making up these crystal inclusions. They're almost always black or gray or possibly a very dark brown in appearance, and they are usually more uniform than in HPHT. You're not going to see the really fanciful rods or blobs in quite the same way. This photo here on the right is not really much to look at, but these scattered black crystals are one of the most common things that you're going to see in the CVD diamonds on the market. This is extremely typical of what we see in our CVD diamonds every single day. That's not to say that they can't have some fun little things though. Here's an example of a couple of crystals with these comet-like tails extending from them. It's really a combination of a crystal and a cloud, but it's always sort of a fun thing to see, and it's something you'll see occasionally in these stones. Now, the next inclusion I want to talk about is clouds. In natural diamonds, much like with crystals, these clouds can have a variety of appearances, but the most common way to see them is this sort of hazy look or a collection of pinpoints. Their appearances can have a lot of overlap with lab diamonds, in particular HPHTs, which we'll look at in the next section. But something to note about these natural diamonds is that when these clouds are light in color, and dense and cover like a large majority of the stone, they'll lend a sort of overall hazy effect to the diamond, and that's something to look out for. And in HPHT grown diamonds, much like in natural diamonds, their clouds are collections of pinpoints, but in HPHT, they are particularly high relief pinpoints. It is common to see them through the pavilion, even in stones where you can't necessarily see them from the crown. On this photo on the right here, you'll see what would have been a VVS1 cloud in a lab-grown HPHT diamond with just these scattered high relief pinpoints in the pavilion. In fact, sometimes you can only really see them around the culet in some of the highest clarity HPHT stones, and that's always something to look out for. The reason that the pinpoints in these clouds are so high relief is because, much like the crystals, these pinpoints are also made of the same flux remnants. And so they are just as metallic and just as reflective. So as you're moving the stone around, the whole cloud can sort of turn from light to dark in the microscope well or under the light with your loupe. And again, much like with the hazy clouds in natural diamonds, if one of these clouds is covering a huge portion of the stone and is very dense, it can also lend a similarly hazy appearance. The clouds in CVD diamonds, though, those are pretty interesting. They can have a lot of different appearances. They can be dark fuzzy clusters. They can be hazy planar clouds. Planar clouds in particular are really characteristic of CVD grown diamonds and are a good way to assist in identifying them. Here's a couple examples of the really typical sort of grainy style cloud that we see. You're not really going to get a hazy appearance with these, and that's because they are so dark, they just stand out in stark contrast. But you can see here this sort of fluffy appearance here, this weird, almost geometric sort of grain. Those are the kind of things that we see really commonly in clouds in CVD diamonds. And for these photos, we have a couple examples of the more hazy planar clouds. These clouds follow the grain of the diamond. Sherry talked a little bit about the creation of CVD diamonds and how it's these layers of carbon getting deposited. And it's this layering effect that causes the grain, and that's why we see these flat planar clouds. As you're tilting your diamond back and forth, you may see them appear. This is a photo of one that you can see under the table. You see this sharp relief, this line here. This one is a little bit less sharp, but no less interesting. It's here at the edge of the diamond, and you can see it actually reflecting in the pavilion. You can see it darker there as well. And as a note, just quickly about the graining, when we say that clouds follow the grain, this is that CVD graining, again, caused by the growth method. And this is something that's super prevalent in CVD diamonds, something you're going to see all the time when you look at them, especially in the microscope, caused by the carbon deposition process. So when we say, oh, there's a planar cloud following the grain, this is the grain that we are referring to. And for the last inclusion that I want to talk about, let's discuss needles. Needles are essentially elongated, very thin crystals that we refer to using a different name. They're pretty common in natural diamonds. They can be found in clusters, and they can be pretty irregular. We have a couple photos here, one of a very interesting cluster that we found of needles in a natural diamond, and then one here of needles that are maybe more typical of what we'd see, just a couple of little scattered ones in a stone here. And in HPHT diamonds, needles are, they're made of flux, just like the crystals, just like the pinpoints that make up the cloud. These are a lot more uniform generally than the needles that we're going to see in a natural diamond. They can often even form clouds throughout a stone or clusters. They can be super long, hair-like, but when you have a lot of these needles in a stone, very often they'll all look really, really similar to each other, despite having variation between stones. So here's an example of a cloud of these sort of hair-like needles. You can see that they're all the same type of really, really long, really thin, almost hard to see needle here, as opposed to the stone on the right, where they're arranged in these clusters. And even though these clusters are kind of irregular, you'll note that in this stone, this is the trend that the needles there are following. And as a note on clusters, actually, before we get there, I have a couple more photos of these needles. This is actually a really good one showing how thick they can be as opposed to the hair-like needles. And they can even form these metallic platelets, which are somewhere almost in between a needle and a crystal. That's a really good example of one right here. They are entirely flat. They're usually triangular shaped, And these are actually one of the best ways to kind of see what I mean when I'm talking about the metallic nature of these inclusions, because they're so flat and wide. As you're tilting the stone, they can really show that like complete reflectiveness within them. And so here are a couple of pictures that you've already seen of the needle clusters next to each other. You'll see that although they can appear similar, these HPHT needle clusters again have this kind of weird looking uniformity that's hard to put your finger on, but is definitely noticeable compared to something a little bit more irregular like this. But you will see clusters in both of these kinds of stones, so definitely something to look out for. If you're trying to separate the two, definitely something that you'd want to look into pretty closely. And with that, I think I'm going to hand it back over to Shari for some questions.
Thank you, Kayla. That was excellent. Really, that was great. Thank you very much. And we do have some questions. So actually one of the questions is, does CVD look a bit oily compared to HPHT grown diamonds? And what is this characteristic called? So actually, I think you just answered that one. You showed a picture of the 360 of CVD, where it showed some graining. So we call this characteristic, at least I think what you're talking about would be called graining. We see graining in natural diamonds, HPHT diamonds, and CVD, but CVD diamonds tend to be have more. It's a little bit characteristic, especially of CVD diamonds that are grown very quickly or in some of the older processes. We see less graining in newer CVD diamonds that are grown today. So thank you for that question. Someone else asked, Kayla, maybe you could answer this one. It says, how often can you tell what type of diamond you have with only magnification?
Sure. That's an interesting question. And the answer is that for someone who is a diamond grader or gemologist who spends a lot of time working with these stones in the microscope, pretty frequently actually, and you have a lot of experience separating them, doing research on them, you get to really understand the patterns that you're seeing, the things that pop up really, really frequently. You'll get an HPHD diamond, you'll immediately be able to identify, for example, that cloud through the pavilion or reflective metallic flux inclusions. You'll get a CVD diamond in the microscope and you'll be able to identify that sort of layered graining that's so characteristic of them. Or you'll get a natural diamond with transparent crystals and be able to kind of clock that right away. Of course, this is always a process with a lot of caution to it. Even in the lab, for people who've been doing this for years, we never, ever, ever identify a diamond only by looking at it through the microscope. We always add other research techniques. But once you spend a lot of time looking at them, you can really get a feel for what you're going to see most commonly with each type.
That's great. Yeah, I'd agree. With experience, you can get a good feeling of what you have. Exactly. Okay, so another question that we have here, the layered growth pattern, is this visible only in laboratory grown diamonds? And what if it's a fancy colored diamond? So I think this is referring to the slides that I was showing about the layered growth that we see when we're using the Diamond View instrument, when we're using very shortwave ultraviolet light, where you can see the different growth patterns. And CVD has a distinct, very layered, or you'll even get, if they stop and start the growth, sometimes they stop the growth of CVD, they take them out, they laser off the edges, clean them, and then they put them in and grow it again. And then we get a very sharp, distinct pattern in Diamond View or with shortwave ultraviolet imaging. And if it's a fancy color diamond, then it definitely impacts what we can see in terms of the UV reaction. So it depends on what color it is, how it's been treated. If it's irradiated and annealed, oftentimes, like in a pink diamond, the fluorescence will be so strong that it's very difficult to see a growth pattern in that. So sometimes we'll use different filters that we can cut back on some of that very bright fluorescence, and try to see what the pattern is. So I hope that answers that question. Another question that we have here, let's see. Let's see. Can you refer to the differences in light performance between CVD grown diamonds in layers to those grown in one shot? So I think that the graining that you see, which you can also see, plenty of natural diamonds have graining that you can see when we're doing the light performance 360 videos, fire videos, these different things. Sometimes you see the graining, like the examples that Kayla was showing of 360, you can see the graining in all different types of diamonds. So I don't think it only shows up in CVDs that are grown in one shot versus one that are grown in multiple. But there definitely is a difference in the quality of different manufacturers. Some have much better quality with, you know, that they're as grown, they're not post-growth treated. It's all grown at one time. There are less, you know, if they take more time, you end up with less grain and better color. The ones that are grown much faster would tend to be grainier and probably browner is what we see.
You mind if I grab one, Sherry?
Yeah, sure, go for it.
I see a question here. It says, why aren't all lab-grown diamonds D and IF? And I think Sherry kind of touched on this briefly. That is entirely due to the growth process. In fact, the longer that it takes to grow a diamond, generally speaking, the higher quality it's going to be. Getting the really high quality lab-grown diamonds is going to take a longer amount of time creating it. So while it's definitely possible, and as we saw with the graphs earlier, we're definitely seeing diamonds like this on the market now, lab-grown diamonds, but it takes a lot more time. And so that's something that manufacturers have to weigh, is the quantity versus the quality of diamonds, because the longer you spend growing a batch of diamonds, the less of them you're going to be able to make. So it's a trade-off.
Great. Okay, so I think that we're just about out of time for today. So I would like to thank everyone so much for taking the time to be here. We're going to send out a recording. We'll send out a link of today's webinar. If you think of any additional questions, feel free to email us it'll come to both of us, webinars@gcalusa.com. And next month, we have a webinar about fancy shaped cut grades on May 15th. And then in June, we have another webinar more in depth about screening and identification. So please follow GCal by Serene on social so you can stay up to date on all of our exciting news. So thank you all so much for being here, and we'll see you again at one of the webinars in the future. Thank you.
Thanks for coming, everybody.
Thank you.